So I've just turned that on now, so we're away. Alright, so let's have a look at what we think is the issue here. And that's got to be cool, right? I mean, that's got to be... what lecture is this? About 6, is it?
I'm sorry, what's that?
What lecture is it? About 6?
5.
5, is it?
Lecture 5.
Yeah,
Yep.
okay. Alright, so I might as well just... that's alright. Okay, so is the notion of a one-to-one okay with you guys?
Yep.
Okay, so the notion of a one-to-one works. Okay. And there's a couple of hints there about that. If a vertical line cuts a graph more than once, so that's the vertical line test. Okay. So obviously a circle is not, these are not functions in terms of x. Okay, so that's just a nice thing to know. Increasing and decreasing have an additional property. For each y value there's only one value of x. Always increasing and always decreasing, so that's not an example, but that one is. Okay, it's always increasing. This one's also decreasing, so these two have a special property that they're one-to-one, or an additional property that they're one-to-one. Besides passing the vertical line test, the one-to-one functions also only cut by a horizontal line once. So that's a definition of a one-to-one function. So that one there's not a one-to-one because that doesn't work, but here it works and here it works. Okay, so those two guys are one-to-one. So whenever you're doing a thing like a look at is a particular function, is it one-to-one? Is it an actual function? Okay, so all the ticks are functions, and the two other ones here that pass the horizontal line test are one-to-one. So what do we think about this exponential function? The exponential function is both what?
It's 1-to-1.
Well, first of all, it is a function.
Yeah.
And it's one-to-one.
Yeah.
Okay. So now that we've talked about that, what's the requirement to be an inverse? So it satisfies this undo principle. See this written language here? You might not have recognised it straight off the bat, but this is in the form of an undo. Now you think about undo the way I've expressed it to you, maybe that makes sense now. In other words, you're taking the function of a function. So it's a bit like taking the sine of a sine to the -1. We've done that before. And you're just left with whatever's there. So in this case here, you're just left with whatever's there. So it's exactly the same idea. So don't be put off by the scientific speak, because it's really not that big a deal. Okay? I think that's a reasonable thing. Alright. So with this guy here, my favourite idea here is to draw y equals x. I've done this with you ad nauseum. And then what you do is you juicy this up, ink it up, and then you crease the page on the thing there, and what will you get? You'll get the mirror image of this. I don't know if you've seen that before, but this is an example of an inverse. So this is the 2 to the x function, and this is the inverse function. I've just drawn it on there to make it the same. Okay, so it's the inverse function. So in that case there, it's going to be the ln of 2, isn't it? it's going to be the log base 2. So this one's y equals 2 to the x. Okay, so it's going to be the base 2. So they're harder ones, because the algebraic ones, I mean, you didn't even do an algebraic version here with this, and you've gone straight to a logarithmic one. So that's a bit cheeky, just putting that straight on. Okay, but so essentially what you get is a mirror in the y-axis. Now you can use your technology if you want to figure out what I've done there. But remember, the standard bearer for all of these things, whenever you encounter anything like this, is to jog your memory, bring it back to this, which is so familiar. Okay, it's also equal to the log base e to the x. Put your inverse in, and we know that one is the ln of x. Y equals the ln of x, or if you like, y equals the log base e to the x. Okay, so the log base e. So these things here, so when you're doing a transform with a less familiar one, always bring back your memory aid, because this is kind of like your bread and butter. Okay, remember that the ln function is the log base e when the actual function is e to the x. Okay, so log base e. So for this one here, that's why I was able to conjure, if you like. I didn't just pull it out of my backside, but you can use technology as well to find an inverse. All right, so what else have we got there? Are you happy with that? Any questions? Keep moving.
Well, just so that you know, Mary had, like, this is the exact thing that Mary did in the lecture. Like, so she did this exact same thing, and
Well,
like she went through this whole sheet.
Yeah, well, that's where you've got to tell me, stop there, I didn't understand that. Okay. So I was only going on what you said initially, because I'm very flexible. So I was only going on what you said initially, which said would be good to go over a couple of examples, which I'm fine with.
Okay. Just, I guess then, the questions on the lecture is probably the good sheet to go
practice
through.
Questions.
Yeah, that's correct. Yeah.
Oh, okay. All right. Fine. That's good. All right. So we'll go here then, and I'll get the practice question. Now, all of them or select? Well, we kind of did the first lot, 1-to-1. What's a 1-to-1? Yeah.
Sorry, I was just going to say, maybe, just start, and then if there are a couple of repeat questions, we can always skip a couple. But yeah.
All right. All right. That's fine. Just let me know when we get to them. Okay. So, what is a 1-to-1 function? Because I'll end up doing that kind of thing anyway. You know, where I'm going over the stuff. So I apologise if I bored you to tears, but there you go.
No, that's all good.
All right. So what do we got? What's a 1-to-1 function? So which one of these suits? So that's an odd way of saying it never takes on the same value twice. 1-to-1 function, if it has a negative slope, well, that's out. Is 1-to-1 if it is a horizontal line? Well, that's out, because it would fail the horizontal line test. 1-to-1 function period takes on the same value. No, that's not it. Okay, so we know that a function is a function if it has a vertical line test, so it looks like it's this one. Okay. All right. How can you tell from a graph that a function is 1-to-1? So the 1-to-1, so it is a function. So its vertical line test is a given. Okay. So it's not that one. So it's got to pass the horizontal line test. So it's always it's monotonic increasing or monotonic decreasing. The horizontal line test will never cut it twice. Okay. So it's got to be A. A function is given by the formula 10 on x, determine whether it's 1-to-1. So this is a variation of a log function. So you might not recognise these, but don't beat yourselves up, right, if you don't recognise a log function. So y equals 1 on x is just the log this kind of thing going on. Okay, and the asymptote's at 0. The 10 is going to have what effect? It's just going to be a multiplier. Alright, so the 10 is just going to be a lot steeper, but it's still going to be located at 0. So where this one was kind of 1, this one will be like 100. Okay, so it's still got its asymptotic at 0. So does it pass the vertical line test? Okay. So it is a function. Well, we've been told it's a function, so that was a redundant question. Does it pass the vertical line test? Yes. Okay, so by doing the vertical line test, you've established that it's a function. So that's good. Alright, just interrupt me if there's a question, alright? Function. So function's cos of x, so it's got the passes the vertical line test, so it's not coming back on itself. Okay, but it fails the horizontal line test. So although it's a function, it's not one-to-one. Okay, so you would say not. Okay, if a function is one-to-one, oh, for God's sakes, what's the inverse? Oh, well, that's probably not as hard as I think initially. So I think the inverse is going to be the other number. So it's going to be -4. So if I have f -4 equals -5, when I do undo, I'll put f to the -1 f -4 equals f to the -1 -5. So I've taken -1 on both sides. This is undo, so you're left with f to the -1 -5 is equal to -4. So that's your answer. So undo works there as well. So that's a bit of a neat way to deal with that, I think. But anyway, the formula where expresses, find a formula for the inverse function. Oh my God. Okay, so the inverse function is simply going to be what you've been taught. You've been taught what? Swap the formula. Expresses Celsius as a function of Fahrenheit, so we want to go for Fahrenheit is a function of Celsius. Okay, so is there anything here I need to be aware of? It's just a straight swap.
I think it's just a straight swap, and then because that will give you the formula for the inverse function, and then we just need to answer the domain question.
Yeah, but I'm just thinking if you do a straight swap, you'll have f equals 59c minus 32. I don't think that's right. So if you just swap the pronumerals, you won't get what you're looking for, because then you'll have f in terms of c, but it won't be, it'll be the c in terms of f function.
You could just multiply out, and then yeah.
Yeah. Okay. Now this tells us something. This sets a minimum value. Well, we know that's absolute zero anyway, or at least the physicist and the chemist amongst us will. Okay, so this one was a bit of an awkward one. Okay, so the domain's going to be, that's the bottom end, and we want it to be inclusive. So in set notation, that would be that one. So it doesn't go off to infinity, it stops at minus 273. Okay. And C goes off to infinity, inclusive. Yeah, that's a bit of a yuck one. I don't like that one. I don't like that one at all. Alright, just be careful swapping, because that puts the variables in terms of the other, but it might not be in the right proportion. Whereas that's the one that works. So you need to be careful about that. Alright, find the formula for the inverse of this one. Alright, so if we did do the xing and ying, so if that's y, alright, then we could write x equals minus 1, 2y plus 3. And what are we solving for? Y. We'll skip the step there because I've times it by. And you'll have to take your y out. Divide by sides. How's that? Now what's the value that makes, what's the great thing about quotients? You can't have the denominator equal to 0. So that's the beginning of limit theory, if you think about it, but anyway, that's another story. So what value can x take on that makes this 0? It'll be 4, won't it? Okay. Alright, so these are killers if you don't know exact values trig. Alright, if you haven't spent time on exact values trig, you're looking at this and thinking you may as well be speaking an ancient language, okay, or an alien language. So if we think about this in terms of sum of value, okay, and we take sine of sine to the minus 1 root 3 on 2 equals sine, because I took sine on both sides of the unknown. I could call it x, but I'm just going to leave that out for the moment. This is undo. Now if I reverse this is more like I taught you. Okay, this is saying what? What's this saying? This is saying what's the angle, what's sine in associative language that I've taught you? Sine, another name for sine is?
Phi.
Okay, so this one's saying what angle is y that length? In other words, what angle is y that length? And there's a few of them, isn't there? Okay, but it only wants the one. So the angle in there is the larger angle, and the larger angle has the smaller denominator. So the answer to this is pi on 3. Now if you don't know what I just did, you need to go and learn that sheet that I did in exact values trig. Okay? Now we can do the same approach here. We can go cos of the minus 1 equals, and I'll make it x, the cos of x. Okay? Therefore, the cos of x is equal to 1. Now I could have put theta, that might have been a more apt. I just wanted to express it as a variable, but maybe the trigonomic variable is a better one. Okay, so when is cos theta equal to 1? So again, exact values trig, the 1's here. Okay, so cos is, associatively cos is?
X.
So this question is actually asking, what's the value of x at where it's 1? And the answer is theta is 0. Okay, so if you want to zoom through your course, you need this exact values trig, and hopefully it's paying off for you now. Hopefully you're feeling pretty comfortable with the whole concept. If you're not, get back and study that sheet I gave you, because it's a winner. Alright, so what do we got here? Find the exact value of each expression. Well, it's the same kind of thing. Okay, it's the same kind of thing in terms of is that a solution that's been put up there, or they want you to fill it in? There are many possible, well, there's not many possible angles, there's a few possible angles, and with this sign, but the range is restricted to, and so it must be in this interval. Okay, so the same kind of thing. We almost did this down here, didn't we? We did do it down here. Okay. Sine root 3 on 2 is pi on 3. So let's have a look at that. Question. Find the exact value for sine. So this is a domain restriction. This is saying that we're restricting the domain. Oh look, that's all very wordy. That's a wordy attempt, isn't it? This is a domain restriction. So it's only looking at from your pi's. There's your pi's. I'll just change pens. There's your pi's. 0. Pi on 2. Minus pi on 2. It's only interested in y between here and here. That's your domain restriction. It's not interested in any of this stuff over here. So the only value is pi on 3. Okay, so the domain restriction is given. So there's nothing mysterious about that. So we got minus pi on 2 and pi on 2 because you gave it to us, you know. And so the value in the interval of minus pi on 2, and the point that's being made there is that you can have any number of rotations, and so when you have a domain restriction like this one, we're only looking at the first and fourth quadrants. So if we look at the two halves, I actually feel like there's been a mistake made in this one, because if we go to just changing the colours, if I do that one, that theta is pi on 3, and that's for that angle, that one. Negative theta will go this way. Negative theta will go this way. But is there a difference there? Did I make a mistake? No, I didn't make a mistake. Okay, so what's the subtle difference between these two questions? Very important. I missed it. I missed
domain
it. No, there's
Is
something
it
else.
just the domain restriction?
No, there's something else. What's the root 3 on 2? And so I picked that one. It's plus root 3 on 2. So this is a good distractor because the question then comes up and it says minus root 3 on 2. Okay, so we can't just jump to the conclusion that we've got to jump to. We've got to do it all again. It's exactly the same idea, and it'll land in the right place for us, but we just need to keep our wits about it. So the given domain is fine, but let's just do the thing with the minus. I'll get my blue one back. So here, I'm going to have sine to the minus 1. I have to do it again. That's the thing I didn't do, because of minus root 3 on 2. So I'm going to pose that question again for some value of theta, sine theta. So they're going to undo, so therefore sine theta is equal to minus root 3 on 2. Okay, so then that is your exact values trig. Where is y negative? Well, y is negative here, that's that one. And y is negative here, that's that one. Now because of the domain restriction that's given, okay, we're only interested in pi on 2 and minus pi on 2. So this first quadrant is actually out. Okay, because there is no negative y up there. There's no triangle up there. So then that leads us to this one here. The only one that we're looking at is this one. So there's two ways to deal with this. We can count. We can go 1, 2, 3, 4, 5, and we can say therefore theta is equal to 5 lots of pi on 3. And if you put your thing in the calculator and do sine 5 pi on 3, you'll get this root 3 on 2 with a negative in it. Okay, now the other one is not included. 1, 2, 3, 4. It's not included because it's outside the domain restriction. Okay, now why isn't the answer going to be 5 pi on 3? Okay, why isn't the answer going to be 5 pi on 3? Because it should be, and I would argue, if you put that answer, I would argue that that's the correct answer. However, if we look at this through the lens of negative thetas, okay, we're only going 1. Okay, so we're only going 1. And 1, count, 1, 2, 3. No, we're not going around, we're just going 1. So therefore, theta in the negative would be minus. The bigger angle has the smaller denominator. So this question is a bit flawed in the sense that down here, if you were to write 5 pi on 3, I believe you would be correct, but I think that's what they're actually wanting you to do. Now, I reckon that's a bit rude because you haven't really been trained in negative angles, and the eyebrows would go up and they would say, well, they should know it. Well, okay, but it's stuff like this that helps you see it. Alright, so if you put 5 pi on 3, and I believe that's the correct one, and just to hit this home, I'm just going to be completely annoying. And I'm going to do the sine thing for 5 pi on 3. So, sine, let's do 5. 5 times pi divided by 3, and take the sine of that. because you've got to be in radians, you numbnuts. Sorry guys. So 5 times pi equals divided by 3 equals, and take the sign of that, negative 0.866. We'll just stick that in the memory for the fun of it. Now let's do minus pi divided by 3 equals, and do the inverse. No, just do the sign of that. There it is, it's the same number, 0.866. So I do memory recall, it's the same one. Okay, so that's the correct way of thinking about this. The counting thing, the only thing that I would say it doesn't apply is because that requires us to count into the domain that we're not counting into. So that's the justification for not having that counted, because we would count into unrestricted domain. But if you don't get taught this stuff, how would you know that? So that although technically the numbers are the same for the 5 pi and 3, the domain restriction means that we shouldn't be counting positively because we're not going to go through. But I don't know, it's a bit of a sloppy question, because I reckon if you get to 5 pi and 3, you're in the right domain. So anyway, I'll leave that for others to debate. Hopefully that solves that for you. So negative angles, probably the answer. Okay, but you've done that with the exact values trig, so you should be happy. Alright, so for this one here, same kind of thing. Now, you know, anytime you see this kind of thing, it's going to be a version of pi on 4, okay, or some such thing. So just to humour yourself, it's worthwhile, before you go on and do any more, just to cos this. So what value of theta gives you root 2 on 2? So it's a scaled angle of 45 degrees, I think. But again, we've got a domain restriction. So that domain restriction means that we're going from 0 to pi only. And are you actually being asked to find that angle? So you told us 0 to pi. So inclusive. So that's the answer for that one. The angle y whose cosine is minus root 2 on 2, and it is y equals. Okay, so it wants the solution now. Okay, so it wants the solution. Alright, so in your exact values trig, when you go just that one, you get 1 over root 2, 1 over root 2, 1, and pi is equal to, now they've done it again, pi is equal to, and theta is equal to pi on 4. Okay, now they've done it again because they've talked about, okay, alright, so if we take those and rationalise them, we'll get root 2 over 2. So that's the unfamiliar form. Okay, so it's this familiar form, but it wants the x that's negative. So it wants the x that's negative. So the x that's negative is one of those two. Okay, it wants the x is negative is one of those two. So which one is it? Well, we've got to look to the pi. Okay, so count 1, 2, 3. So I'm saying that the angle's that one. So that's the one of interest. And that is, theta is pi on 4. But it's 3 lots of pi on 4. So it's equal to 3 pi on 4. Just be careful of how you write and count. Okay, I don't know how else you can do these things without doing exact values trig. You can do it all stations to central, but you're going to do your head in when you do inverses, so I wouldn't be too worried about that. Alright, any questions about that? We happy with that? Okay. Alright, so the exact value of these expressions, again, it's going to be the case that you just need to go back to your basics and think about what's being asked. Alright, so if we take 10, arctan is 10 to the minus 1. It's just another way of saying it. So if we take 10 to the minus 1 of root 3 equals theta as a variable, equals, tan theta, we can say tan theta is equal to root 3. Now in actual fact, tan theta is rise over run, which is y over x, which is root 3 over 1. So if we draw a little triangle and y is root 3 and x is 1, okay, this goes back to a scaled version, okay, because if you do this one, I want to make that more exaggerated. If you do this one, and you're supposed to recognize that, if you times that by 2, you'll get that one. So it's a scaled up one, but the angles don't change. So this is really saying, what's that angle? And we know it's a 30-60 triangle. So just by recognition, that's a 60 degrees. The bigger number has the smaller denominator. Alright, so if you haven't been trained in exact values trig, this is a horrible section. This is a horrible part of the subject. Okay, so it's really, really valuable. It kicks home a lot, exact values trig. Okay, same kind of thing. This is going to be a 45 degree. It's going to be the negative one. So the negative one probably implies, without the main restriction, that we go for this one. Same angle. Okay, so that angle there is 0 in the negative. So we count 1, so it's going to be 1 lot of pi on 4. And you go through the whole thing again, you can do all that again. Just to satisfy yourself that you're answering that question. When is y? Well, it's here. It's there. I probably don't need to keep doing it, but it's there. Okay. When is y negative? It's also here. It's also there. So in this question, because we're taking the inverse, it's just looking at the negative quadrant. Okay, so whenever you see the inverse, just take the negative angle. Alright, the graphs are given. My sheet must not have got it.
It just says graph the given functions, not that they're given.
Y equals x. Why are we doing y equals x? Because y equals x is an inverse. Okay, the sine part of sine is going to start here and go off like this and come down here like this. So that's sine. Now the inverse is going to be a reflection. Okay. So how are they related? Sine and sine to the minus 1. Okay. And what does that tell you? They're inverses. I mean, it's a pointless statement because you're given it, but yeah, sine to the minus 1 is the inverse of sine. That's a geographic interpretation, that's all. Alright, let's go here. Can I go away from that? You happy with that? Just
Yep.
shout out if you need me to pause. Alright, so find the derivative of the function simply if possible. Simplify if possible. So sine to the minus 1. Okay. So y equals. Now how have we done this in the past?
Just on the sign in front. Yep.
I don't like the answer you're going to get. Okay? I'm not happy with the answer that you're going to, the way that, I mean the answer will be the same. Alright? But implicit, I'm doing implicit. The answer that you're getting is not. So with respect to x, so we'll get d dx sine y. How's that work? D dx 3x plus 5. Well, that works. That makes perfect sense. D dx 3x plus 5 is just 3. D dx of sine y doesn't work, but we need d dx. So we're invoking the chain rule. And the chain rule is going to be the one that makes sense. So that now makes sense. Okay, so d dy of sine y, differential sign is cos, dy dx equals 3, and so dy dx, or y dash, is equal to 3 divided by cos y. Now we're out of step here because cos y is not x, so we've got to go back up somewhere and fish something out. So we go, I much prefer this. Okay, I'm sorry to do that to you. It's different to what Mary's doing here, but I feel this has got more power in it for you for your mathematical sciences, and Mary could correct me on that if she wanted to. We want cos, so cos squared y something is going to be equal to 1 minus sine squared something. So cos something is going to be equal to square root of 1 minus sine squared something. Now up here we can say that sine squared y is equal to 3x plus 5 all squared. So that's a substitute for that. So cos something is equal to the square root of 1 minus 3x plus 5 squared. Now this is a harder version, but doing this technique, I haven't changed anything in the 6 or 7 times I've done it with you, and it just works as far as I'm concerned. Okay, so now we can stick a y in there. Okay, and so we've got 3 over the square root of 1 minus 3x plus 5. Now I think if you do it the other way, the way that's going to be suggested to you, that is mucking around with you, it requires you to know something, okay? And if you don't know it, you're in big trouble. Alright, so to help try and lay that bare, if I were to write u equals 3x plus 5, so now I'm doing a different method. If I were to write u equals 3x plus 5, then y would be sine to the minus 1 u. Now in your explanation, it simply goes to this. Okay? Now I want to know if you know that. I've taught you it doesn't matter. All of this is the same method over and over and over again, and it works. So if you didn't recognize that that is that, this is a big problem, doing it this way. Okay, but I'll leave that for you to judge and for you to work through. Okay, so differentiate the function log base 2, 7 minus 4x. Okay, so how do we deal with this? A change of base formula is probably the simplest way to do it. Okay, a change of base formula takes this one up and changes it to the natural logarithm. See that change? Remember, ln is equal to log base e. Okay, so the change of base formula, and then you've got to take the log 2 down the bottom, and so it becomes ln of 2. So this is the change of base formula. Okay, once you've done the change of base formula, then you can just do a quotient differentiation. Okay, and the rest is pretty much straightforward. That's a chain rule. So I'll let you do some work there. Alright, so any questions? Can I keep going? Now with this guy here, the log laws are going to play a part. So as a bit of pre-work, you might want to consider changing forms. Okay, so this is saying the 6th root of something. So when we've got something and we've got the square root of it, it's the something to a power of a half. Sitting in the nape of a square root is 2. The 2 goes on the denominator of the fraction. So that 6 is going to go on the denominator of the fraction. And because there's no power here, and the power normally sits there, it's just 1. That's how we would read that normally. Okay? So that 1 sits there, and that 1 sits there. But we never write something with a power run of it. We never write it that complicated. But that's the maths behind it. Okay. Alright, all those little bits. So what are we going to have? We're going to have the ln of x to the power 1/6. I mean, I'm just going to try something here. Yeah, I might just leave it. Alright, so I suspect that what's been taught to you is to then go ahead and take into account the fact that the logarithm's there. Okay, and the ln of x is 1 on x, the differential of the ln of x is 1 on x, is it not? Okay, so all that's happening here is that you're going through the same kind of process. So you bring the 1 on 6 out, minus 5 on 6, divided by x 1 on 6, and then when you put it all together you'll get 1 on 6x. So I'm not sure how that's been unpacked for you in your videos. I haven't looked. To be honest. I should have probably had a look at that. So generally speaking, if you've got something like, I just want to grab a file.